Hello, folks. Good morning, good afternoon, good evening to all the people all over the world who've tuned in for this AFuzion BUGSEng webinar on MISRA C. So we have an action-packed hour for you here, and we should have a few minutes for questions at the end. So we will be sending out a link to the recording. You can watch this recording at any time, and we'll have a few minutes for your questions at the end. Right now, it's my pleasure to also introduce Mr. Roberto Bagnara, who's the CEO, CTO, and Chief Scientist of BUGSEng, based in Italy. So we're going to begin right now. And as you know, I'm Vance Hilderman, and we do these monthly technical training webinars, and they become increasingly popular. So it's always a pleasure to have all of our people tune in. A quick background information for those of you who don't know about us. AFuzion is a company based in the US, but we work all over the world. We have over 250 safety critical projects currently underway or recently completed in the last 3 years. And we work on-site, off-site, typically aviation, medical devices, automotive, any area where we have safety critical certification development going on. And we have 45 engineers who focus on process optimization. We have templates and training checklists for various industries. We also perform mentoring, auditing, and in total, we have over 300 total successful safety critical projects, and 100% of the clients have said they either have or will hire us again. Roberto, would you like me to introduce you for a quick introduction of yourself on BUGSEng?
Sure. So BUGSEng is a supplier of tools and services for software verification. We are based in Italy. We have 2 sites, one in Parma and the other in Pisa. And our solutions are built on more than 20 years of scientific research. So everything started at the University of Parma in Italy. Our main product is the Eclair software verification platform, which is qualifiable for DO 178C and other functional safety standards. We also provide services concerning software verification, consultancy, and we do also training.
Very good. Thank you, Roberto. Well, folks, let's go ahead. And you know how our training sessions start on these technical monthly webinars. First, a quiz. Here on page 3, 6 true-false questions. Number 1, software testing is the best method to improve quality. Many people think so. And by the way, we'll provide the answers to these in about 45 to 50 minutes once our primary technical training is done. Question number 2, true or false? Safety critical domains provide good information and recipes for developing C code. Number 3, humans, that's you and I, are effective and efficient at reviewing and optimizing C code. Now, most of us think we are. Number 4, true or false? With great static code analysis, no other software verification is necessary. Number 5, dynamic software testing is similarly efficient and effective as static analysis. And the last question, number 6, verification and validation are similar. That's why it's called V&V, right? Well, let's see how you do. 6 questions, 6 answers, coming up in 45 minutes. Now, let's summarize safety critical. What is it? Well, a safety critical system is a system that if it should fail or produce anomalous behavior, malfunction, it could result in one or more of the following things happening, and none of these are good. Death or injury to people, loss or severe damage to property, equipment, or environmental harm, sometimes all 3 of the above. So when it's safety critical, there's extra things we need to be aware of and take into consideration. And what we want to be concerned with is, as it's safety critical, what's its reliability? How critical is it? How reliable does it need to be? So software reliability is the probability of failure-free, no anomalies, software operating for a specified period of time within a designated environment. And for safety critical systems that contain software, software reliability is an important factor affecting system reliability. So what happens with safety critical engineering? Well, there's a framework of essentially three critical, what we call integral processes, okay? Number one is the planning process. It comes first. It's important. That's why it's in red, and it's first left to right in English here, where I'm broadcasting from America. Next comes the software development itself. That's the coding, right? No, it's actually the requirements first, the design, architecture, and then the coding to implement the requirements via that architecture. And in the background, the third set of integral processes, verification, validation, configuration management, quality assurance. These occur continuously to assess the plans and the development environment. These are the things that AFuzion helps companies optimize, and we work with them to be more efficient, productive on the safety critical front. Now, before I turn it over to Roberto to dive into MISRA C, for safety critical software, remember there's a pyramid. We call it the 4 pillars. It's really a pyramid. The foundation of that pyramid is the requirements. Those include safety requirements, system requirements. Different domains might have high level and low level requirements, but we define those, and then we develop on top of that an architecture, a design. That's a framework of how the software is put together, not what it does, but how it does it, okay? In terms of calling sequences, objects, methods, internal interfaces, and then the code. That's what we're here for today, the big white one. That's right, it's white box. You got to open up the code to look inside, not black. On the top is V and V. We'll talk real briefly about that. But coding is really the key, okay? Now, what would be necessary to perform a safety critical code review? Not some hacker code, but some true code that was safety critical. We needed reliability like we discussed. There are 6 inputs to a safety critical code review. And that's where we dive in to a little more depth, because in the old world, or the hacker world, you can simply look at the code and assess it. And there is some value in that. But the real question is, what should the code do? How does it do it? And is that appropriate? So there's 6 inputs needed for a safety critical review. If you're missing one, no problem. Do it again when you have all 6. You know the 6? Let's see. Number 1, the source code. Gotta have it. Number 2, some form of checklist that you're going to assess that code to. You need a coding standard, and that's where MISRA comes in, okay? Roberto's going to go deep into the detail in just 1 minute. You also need to consider the software design, because the design is the bridge between the requirements and the code. So of course you need the requirements, and then a trace matrix to tell you what are the associations between the requirements and the code that you're reviewing. Which of the requirements is that code supposed to implement? Then you complete the review, denote any action items or defects, and feed those back into a re-review. That's the transition, okay? Our focus today is on that critical, safety critical coding standard, okay? It's based, the most popular standard, on MISRA. And MISRA was a C subset that was originally defined by the United Kingdom Motor Industry Research Association. That's the basis for the name MISRA. Today, it's an international organization. It comprises, MISRA does, approximately almost 200 rules, okay? And Roberto will describe what those rules are. They're presented in the form of a coding standard. So, without further ado, I'd like to turn it over to Roberto and make him the presenter, so Roberto can go into the details of MISRA C. Roberto, you are now the presenter. Enjoy.
Okay, so can you see my screen now?
Perfectly, and we hear you perfectly as well.
Okay, so let me, yes, go here. So here is the outline for this part of the webinar. I will first say something which is quite important about the C language, and in particular the fact that it is not completely defined by the standard. And I will explain why it is not fully defined. Then I will go on presenting MISRA C. I will present the guidelines by showing some examples, and then I will focus on the essence of MISRA C, which is not about bug finding, not about finding some bugs, but it is about prevention. And then I will give a short MISRA C static analysis demo, and I will show how it can prevent several bugs that have been appeared in newspapers in the last years. So first, a disclaimer, I am a member of the MISRA C working group and also of WG14, which is an ISO committee that standardizes the C programming language. However, the views expressed in this presentation are mine and not necessarily the views of the working groups. Okay, so let's start with the C language. So the C language is almost 50 years old, and it is very popular, and for very good reasons. There are very strong economic reasons behind its very wide adoption. So first of all, C compilers exist for almost any processor, from tiny devices to supercomputers. C compiled code is very efficient and without hidden costs. It allows writing compact code because there are many built-in operators and the language is not very verbose. So it's defined by an ISO standard. Possibly using popular compiler extensions, it allows easy access to the hardware, and it has a long tradition of usage, including in safety-critical systems. And C is widely supported by tools. So there are several advantages, but there is a downside. So the C standardization committee has always been faithful to the original spirit of the language. And the original spirit can be a little bit joking, summarized by these commandments. So trust the programmer, let the programmer do anything wanted, and speed. And speed is more important than portability. And many of these things are bad for safety and security. So let us see what is the problem. The problem stems from the notion of behavior. So for the C standard, now I am quoting the C99 standard, which is the most used version of the language today, even though many projects still are on C90. So the notion of behavior. Behavior is something that is externally observable. So if it is not externally observable, it's not a behavior. And the compiler is allowed to, the compiler actually uses the as-if rule extensively. And this rule says that the compiler can do any transformation that ensures that the observable behavior is preserved. Anything that is not observable can be changed by the compiler at will. Okay, so when I increment a variable x by 1, unless x is a volatile variable, this is not observable from the outside. So the compiler might or might not do it, depending on what is best for optimization. So this is true not just for C, but for many other languages. It is true for all languages that admit an optimized compilation implementation, because in this freedom for the compiler, in this as-if rule, we have most of the optimization opportunities of the compiler. So several of the behaviors of the language are not fully defined. Some are completely undefined. The class of undefined behaviors are those behaviors that arise when you use erroneous program constructs or erroneous data. And in this case, when the behavior is undefined by the standard, anything can happen. So the standard does not impose any requirement, meaning absolutely no requirement. So anything can happen. Okay, the program can crash, it can exhibit erratic behavior of any kind, and it may even format your hard disk. So This is what is said to people that don't get it. It's a bit of an exaggeration, but if your disk is formatted, you cannot complain because it's undefined behavior. What happens is that the compiler assumes undefined behavior does not happen. The C language has been designed so that the responsibility for not having undefined behavior is on the shoulders of the programmer. If undefined behavior is present, then the programmer has violated the contract and there is no warranty whatsoever. Let us see undefined behavior by means of an example. One of the many undefined behaviors is when a program attempts to modify a string literal. A string literal is just a string constant, so a sequence of characters that you write between double quotes. So here we have a small program where we have a string literal containing 3 exclamation marks, and the programmer thought of neutralizing 2 of them by writing a null terminator in position 6 of the string. However, this is undefined behavior because the program is attempting to modify a string literal. One of the reasons behind this undefined behavior is that string literals may be allocated in read-only memory. And when you try to write them, what may happen is another exception that, from the program point of view, has a behavior that is completely undefined. Another class of non-defined behavior is unspecified behavior. This happens when there are 2 or more possibilities to implement one thing, and the standard leaves complete freedom to the compiler. Complete freedom means that the compiler can choose in any instance of the unspecified behavior what to do, which of the possibilities to adopt, without any requirement to document this behavior in the compiler manual, or without any requirement for the compiler to be consistent. Again, let us use an example. One of the behaviors that is unspecified is whether in an addition operation like this one, whether the left-hand operand or the right-hand operand must be evaluated first. So this is unspecified. So this small program may print hello world, which was probably the intention of the programmer, and this happens when the compiler generates code to first evaluate the function hello, and then to evaluate the function word. However, since this is unspecified behavior, the compiler may well decide that word is called first and then hello. In this case, the output would be word, exclamation mark, hello blank, which is probably not what the programmer wanted. But as this is unspecified behavior, the programmer cannot complain. The choice made by the compiler can change completely by, for example, changing the optimization level, or by compiling for debugging or compiling for release. And the compiler, even if I can complicate this example, instead of returning immediately, I can compute 5 times this addition. And the compiler needs not be consistent. So in the first evaluation, the compiler may call hello and then word, and can do it the other way around for the second call. So there is no requirement about this. And then there is implementation defined behavior, which is something that I will not explain because everybody knows this. Everybody knows that there are implementations of the C programming language on 16-bit machines where int is 16-bit, and for 32-bit machine where int is 32-bit. So the size of the basic data types is implementation defined, and there are actually more than 100 implementation defined behavior. So this is a problem. It is a problem if programmers are not familiar with the implementation defined behaviors of their compiler with the options that they are using for compilation. And it is also a problem for portability. Okay, why is C not fully defined? we have seen that there are several classes of non-completely defined behavior. And actually, there is a fourth class, locale specific behavior, which I skipped because it is not so important for this presentation. So why is the standardized language not fully defined? The answer is that because implementing compilers is easier. Not only this, implementing efficient compilers is easier. Compilers that generate fast code. Let us try to understand why this is the case. So let us consider again the undefined behavior concerning the modification of string literals. Okay. Another reason why there is undefined behavior is that a compiler may merge the representations in memory of the string literals. For example, if we in a program we have two literals, one is tail and the other is head tail, the compiled program can store in memory only head tail and use a pointer to the fifth character whenever it needs a representation for tail. So if you change one string literal, you may change also the other one. And the compiler can assume this will never happen because the compiler is allowed to merge for optimizing the space required by a program different literals. So for this undefined behavior, we have seen two scenarios. First scenario, the literals are stored in read-only memory, and when you try to write to one of them, you get another exception. And in the other case, there is no other exception because the string literals are stored in read-write memory. However, when you change one, you may change others without realizing this. Let us move to another example, which is very instructive. So it's undefined behavior when an expression is shifted by a negative number, so when the shift count is negative, or when the shift count is greater than or equal to the width of the promoted expression. So it's easy to understand why shift counts that are negative are undefined behavior, because if they were allowed, we would have to assign a meaning to them. So, for example, shifting a quantity -2 positions to the left, what it might mean? It might mean shifting it 2 positions to the right. But if this was the definition of the language, then the compiler would have to insert for every shift code in the compiled code to check whether the shift count is negative. If it is negative, it would have to negate it and to reverse the direction of the shift. And this is not in the spirit of the language. The spirit of the language is do things fast. So you don't want to play with negative shift. If the programmer wants to play with negative shift, the programmer himself or herself will write the code to deal with negative shifts. So it's a little bit more interesting why it is undefined behavior to shift a 32-bit quantity 32 positions to the left in this example. And one would say, well, shifting to the left means pushing zeros to the right. If I push 32 or even more zeros to the right, the result would be 0. No? No. And the reason is that there are very popular architectures, such as the Intel ones, where the first thing that happens to the shift count is that it is masked. Only the 5 low-order bits are retained. And this is done because this way it is much easier to associate a worst-case execution time to the shift instruction. So on these machines, shifting by 32 positions is the same as shifting by 32 position masked, which is the same as shifting by 0 positions, which is the same as doing nothing. So again, C leaves this behavior undefined for speed and ease of implementation, meaning that a guiding principle of the C programming language is that whenever it is possible, an high-level constructs of the language should be mapped to one machine instruction. Okay, and since there is variability between the machine instructions, this is one important reason why we have behaviors that are not completely defined. Let us now move towards MISRA C. Here is a picture that explains a little bit the history of MISRA C. At the beginning, there were Ford and Rover that were developing their own in-house coding standards for C. So they joined forces in a project that was called MISRA, and this generated the first version of MISRA C in 1998. And MISRA C, the first edition, actually influenced all the coding standards for C and C++ that came afterwards. We are now at MISRA C 2012, which is not 8 years old, meaning that it is continuously updated via amendments, corrigenda, and so on. So the first thing, the next thing to be understood is that the strong point of C and the weak point of C have the same origin. So they are not easy to separate from one another. For example, as I have shown, the ease of writing efficient compilers for almost any architecture is one of the reasons behind non-definite behavior. The fact that you can write efficient code with no hidden cost, it's one of the reasons is that there is no runtime error checking whatsoever. So if you want to check that your index is not exceeding the bounds of an array, you, the programmer, write the check. The language doesn't provide this check for you. The fact that there are many compilers, and despite this, the language is defined by an ISO standard, this is another reason behind non-definite behavior, because the ISO working groups standardize existing practice. So if there are two compilers doing the same thing in different ways, then the only way forward in some cases in the committee is to introduce non-completely defined behavior. Okay? The fact that it is easy to access the hardware is the same reason why it is so easy to corrupt the program state, for example, of overwriting the stack. The fact that you can write compact code can be easily abused by writing completely obscure code, and also there are so a programmer must be trained very well in order to know all the dark sides of the language. So several features of C conflict with safety and security. What is the solution? The solution that was chosen by industry is called language subsetting. It means that you do not program your critical applications in C, you program them in a subset of C where the chances to commit potentially catastrophic mistakes are very significantly reduced. Language subsetting is mandated or recommended by basically all safety and security related industry standards, so starting with the 0178C, ISO 26262, and the others. And today, the most authoritative language subset for the C programming language is MISRA C, and that is why we talk about it today. So let me present some of the guidelines that will give you an idea. Before doing this, I will explain a little bit how MISRA C 2012 is composed. So there are 175 guidelines, and every guideline is either a rule or a directive. There is a slight difference between them. So for a rule, it's the information about whether the code is compliant or not is contained in the source code and in the implementation defined aspect of the toolchain. So the code alone means nothing. So if you have a piece of code saying that A is an integer variable int, you have no idea whether this might be 16-bit or 32 bits. It depends on the implementation. So because it is an implementation defined aspect of the tool chain. So for rules, when you know the code and when you know the implementation defined aspect, you can, in principle, decide whether a piece of code complies with the rule or not. I'm simplifying a bit. For a directive, the information is not completely contained in the code and in the implementation defined aspects. You have to take into account the requirements, the specification, and the designs, and sometimes even the programmer intention. So for a directive, a tool cannot by itself check compliance. It will need the extra information about requirements, specification, and so on to help the programmer. We will see an example later. So the MISRA C guidelines are given a category. The category is either mandatory, required, or advisory. Mandatory guidelines, well, for those, you really have to comply. If you do not comply with the mandatory guidelines, the project cannot make a claim of MISRA compliance. In general, the mandatory guidelines result in things you have that are directly result into big mistakes, and such that there is no valid reason to violate them. If the category is required, then there is a choice. The code can comply with the guideline, of course, but it can also raise a deviation. So a formal deviation is a document explaining why it is required to deviate from the guideline, and why it is still safe to do it, and so on. So you have to motivate in front of a peer that, yes, you are violating a guideline, but the safety of the project is not endangered by this. Advisory guidelines are recommendations. So they have to be followed as far as it is practical. Formal deviation is not necessary if you violate them, but all the non-compliances should be listed at the end of the project in a claim of MISRA compliance. So let's see a selection of three guidelines. So I will start with rule 1.1. It says, the program shall contain no violations of the standard C syntax and constraints, and shall not exceed the implementation's translation limits. This is required, and it applies to all the versions of the C standard language. So this is surprising at first sight. One might say, well, isn't it that the task of the compiler to check whether I am violating the syntax or constraints? Well, not necessarily. Yes, in principle it would be, but things are more subtle than this. There is also another reason. So when a feature is outside the supported version of the chosen C standard, well, these features have not been considered when developing the MISRA guidelines. So if you use something that is outside the MISRA guidelines, do not have the effect that is wanted. So. And another important thing is that even if an implementation, even if a compiler is fully standard compliant, the compiler does not need to generate a diagnostic when a translation limit is exceeded. And since there is not this obligation, then the compiler may still generate code that doesn't work as expected. So the translation limits are and every program has limits. Okay, so there is no compiler on earth that can compile, I don't know, a program that is 1 terabyte of source code. It's probably impossible. There are several such limits. For example, the length of identifiers, the number of cases in a switch. There is a translation limit for this. So the portion of identifiers that is considered to be significant. And so there are several translation limits, and the compiler needs not give a diagnostic. So that is important to have another tool, a tool different from the compiler, that will tell you if you are exceeding one of those limits, because you cannot trust the compiler to give you a diagnostic. And there is more to this. So there are a lot of implementations out there, a lot of compilers that technically speaking are not conforming to the standard because they accept things that they shouldn't accept. They accept code that violates constraint in the standard, and then it is questionable about whether they produce code that makes sense or not. So let's move to rule 3.2. It's a rule about comments. I've chosen it because the first reaction might be, what might be the problem with comments? Well, comments are dangerous. There are 2 or 3 rules in MISRA C dealing with comments. This is one of those. It says that line splicing shall not be used in / comments. So line splicing is when you use a backslash at the end of line, and this will cause 2 physical lines to be merged into a logical line. And the reason behind this rule is that if you mix line splicing with / comments, the risk is that you may inadvertently comment out important code. Here we have an example. We have a / comment that ends with a backslash. So critical function, which is in the following physical line, actually will end up in the same logical line. And later stages of compilation will not even see the call to critical function. So this is a problem. Rule 13.2, it says that the value of an expression and its persistent side effect shall be the same under all permitted evaluation orders. I've already talked about unspecified behavior. This is a guideline that is meant to prevent unspecified behavior, but it also prevents some important undefined behavior. So, for example, when you modify 2 or more times an object in between 2 sequence points, this is undefined behavior. So, for example, if you write I++ plus I++, this is undefined behavior. So let's see another example about unspecified behavior. Here we have an example program that is violating the rule. Why? Because there are 2 variables which are volatile. So reading them can trigger side effects that are externally visible. And since the order in which the arguments of a function call are evaluated is unspecified, we don't know which side effect is triggered first. So in order to comply with the guideline, one possibility is to introduce 2 temporary variables, so to force the sequence of events in the way that we want. And this introduction of temporary variables will typically any decent optimizing compiler will don't let you pay for these 2 extra temporary variables. So let's move to this part of the webinar where I would like to stress the fact that MISRA C is about error prevention and not bug finding. So first of all, MISRA C cannot be separated from the process of documented software development it is part of. And the use of MISRA C in its context is radically different from bug finding. Starting, first of all, the violation of a guideline is not necessarily an error. For example, there is nothing which is intrinsically wrong about converting an integer to a pointer. And in some cases, it is also necessary because you needed to work with memory mapped registers or other features. However, the conversions between integers and pointers are implementation defined, and there are undefined behaviors associated to them. So there is a rule in MISRA C that suggests avoiding them everywhere apart from the very specific instances where they are both required and safe. The deviation process, so the process whereby you might decide not to comply to a guideline in a certain piece, in a certain part of your code, is an essential part of MISRA C. And this is so because the point of a guideline is, apart from the mandatory guidelines, is not you should not do that. The point is, look, this is dangerous. You may only do that if it is needed, it is safe, and if you can quickly convince a peer that it is both needed and safe. So if it takes 30 seconds to explain to your peer why it is needed and why it is safe, it's okay. If it requires 30 minutes, it's not good, okay? And in fact, one useful way of thinking about MISRA C and the process behind it is to consider MISRA C as an effective way to root out most C language traps and pitfalls via a guided peer review. So in an ordinary peer review, you will sit with your colleagues in front of the code, and using MISRA C, you may have your colleagues, but you will also have the output of the tool, and the tool will pinpoint things that are potentially very dangerous. And so it will tell you, look, you know this, is this wanted? Okay, I will give example in the small demonstration I will do in a minute. So another aspect that places MISRA C in a different camp from bug finding has to do with the importance that MISRA C assigns to reviews. Code reviews, reviews of the code against design documents, reviews of design document against requirements. And in fact, many MISRA rules have to do with code readability and understandability. So let me give you this small demonstration. Here I'm using Eclair, which is our static analysis tool. So I will not, the point is not to show you how the tool works. I will go straight to the analysis results. And I have analyzed a very small piece of code where I have collected several errors. So of course, these have been committed intentionally, but they are errors that have occurred in the past and that they are very famous. So let me start with the directive 1.1 of MISRA C. It says that any implementation defining behavior on which the output of the program depends shall be documented and understood. So, for example, how many bits are there in a byte? So yes, most often there are 8 bits in a byte, but there are implementation of C with 16-bit bytes, for example. Okay, so the tool here, this is an example of directive. It is clear that the tool cannot check whether you have documented, let alone understood the implementation defined behavior, but the tool can list the among the more than 100, there are 112 in C99, for example, from how many your program definitely depends and from how many it might depend. And the numbers are here. So this small program depends on 12 implementation defining behaviors, and it possibly depends from another 18 of these behaviors. So I have to document 30 of them and not 112 of them, which is advantageous, of course. Let us see another directive. It says, directive 4.6, it says that you should use type defs that indicate size and silentness instead of the basic numerical types. Okay, here int means nothing. So int means something only with reference to a particular tool chain with certain options. So the advice of this guideline is to use identifier like this one. So int 16t, which is a type def provided by stdint.h, one of the standard header files, which contains an indication of silentness and of the number of bits. Okay, so 4.6. Next one is 4.7. it's a directive. It says if a function returns error information, then that error information shall be tested. Okay, so it's a directive again. The tool this applies not just to the library function. It applies also to other functions. So that this is the very reason why it is a directive, because the tool, if it is well done, knows about the standard library functions, and we can see it here. For example, for scanf, it knows that scanf may return EOF, okay? And here instead the return code is ignored, and printf can also return a negative value in case writing did not succeed. So so the violation says, look, you are ignoring the return values, not just this, but you are not handling the error component of these return values. 4.11, the validity of values passed to library functions should be checked. So checking the return is good, but preventing the errors is better. So, and this guideline says you should check the values you are passing to library function when these library functions do not work for any inputs. This is the case for the absolute integer absolute value function that is called here. It is depending on the representation used for signed integers. In this case, it is 2 complement, and abs is not defined when you try to compute the absolute value of the most negative integer. Okay. So this was 4.11. 4.14 says there is a guideline that has been added to MISRA C 2012 to cover security. So the principle is that you should never trust values received from external sources. In this case, scanf. We have seen scanf might return an error value, but it also receives a floating point value from the external world. And you see that the code here is not testing D. So it's not testing, it may end up to be an infinity or not a number or other things. Okay. And here, the output of the return value of get char is not tested about being EOF or not. You see here, okay, this gives me the opportunity to show you how a tool can do the right thing or not. You see that here in the original code, it's not obvious that key input hides a call to get char, but the tool shows you the code before preprocessing and after preprocessing. So you can see here that there is actually a call to get char. Okay, so rule 2.1. Okay, it says that this evaluation of local variable x is unreachable. You will recognize immediately that here we have an instance of the Apple's SSL go-to-fail bug. You see that due to the fact that there is a repeated go-to-fail here, this code here is unreachable. So you see that in this rule will help prevent this kind of mistakes. Rule 2.2. The value stored into X is not used. So this rule saying that you shouldn't have dead code. So dead code is code that is that it can be removed without affecting the program meaning. And the reason is that dead code is often unintentional and can reveal that there is a misunderstanding on the part of the user. And in fact, this is the case. The fact that this initialization of X is shown as dead code is one of the ways in which we can discover that here we have made a mistake. What is this mistake? This is common weakness enumeration for 8.1. It's when, because we omitted an equal sign, we have an assignment here instead of a test. There is a reason why we have a dead store here, because X is always overwritten. So the fact that we have initialized it with D is useless. Okay, so 8.3. This is interesting also because here there is no way the compiler can give you a warning. What is the problem? The rule says that all declaration of an object or function shall use the same names and type qualifiers. Here we have two different translation units, P.C and Q.C. In P.C, it is said that the function called QUX takes a 16-bit integer, whereas in this other translation unit, we have a 32-bit integer. And since they are in these two incompatible declarations are contained in two different translation units, the compiler can do nothing about this, and the linker doesn't receive the type information. So the linker will link, and we have an undefined behavior. The rule says that not only the functions shall use the same type qualifiers, but they also shall use the same names. Here we have another violation where the types are the same. It's float in both cases. However, the names are different. And notice how I conceive this example. So in one instance, we have that the names that this is a delay expressed in milliseconds, whereas in the other, it's a delay in seconds. So this may happen because two or more programmers are working at the same code. One is working at P.C, the other is working at Q.C. They don't talk to each other enough, and they make incompatible modifications. Okay. Okay, 8.6, here we have a function that is declared and it has no definition, so not big deal. Here is an instance of the Ariane 5 bug. The rule says the value of an expression shall not be assigned to an object with a narrower essential type, so with less bits, or with a different type category. Here we are assigning a floating point value to an integer, and the integer is not guaranteed to contain all the possible truncations or rounding of the floating point values. So this is captured by this rule. This was the Ariane 5 bug, which was caused by an overflow when converting. Actually, it was a 64-bit floating point numbers to a 16-bit signed integers, like in this case. Okay, so we have seen 10.3. Let's see 10.4. This is also interesting. It says the rule says that whenever you are that both operands of an operator in which the usual arithmetic conversion are performed shall have the same essential type category. And here we have a violation, and the tool is explaining very well what's happening. So the first argument of the comparison is 16-bit signed, and 0 is a macro that expands to an unsigned integers. So, and mixing signed with unsigned is a recipe for disaster, because the implicit conversion of C are such that the signed value will be converted to the unsigned type. So a negative value would be converted to a large positive value. And this is the reason why this comparison is always false. Okay. Okay, so 12.1, the precedence of operators within expression shall be made explicit, so we should use enough parentheses. And it is one way where we notice that something very wrong happened. It's not apparent here when we look at the code before preprocessing, but when we look at the code after preprocessing, then we see what's going wrong. So the intention of the programmer here was to take a delay expressed in seconds, add 1 more second, and then convert the result to milliseconds using this macro. However, the macro has not been well written, as another violation will tell us, so that the multiplication by 1000 only affects the one constant. It does not affect the result of the addition. Okay, here is the definition of the macro. So the macro should have had parentheses surrounding x in its body. So the fact that they are not there, it's the reason why we have this problem. So 13.4, it's a rule, another rule that allows us to capture to realize that we have made a mistake here in the comparison. So this was meant to be a comparison, however, it is an assignment. And the rule says you should not use the result of an assignment operator. So, and one of the reasons is to capture this quite common programming mistake. Okay, 14.1, it says a loop counter shall not have essentially floating point type, and the reason is that floating points are affected by rounding, and this is it causes the fact that the number of iterations is if you use a floating point counter are not easily predictable, and in this case, for example, the loop may go on forever despite what the programmer might have thought. 14.4, it's another of the rules that prevents this kind of mistakes. It says, and if then else, the condition needs to be Boolean, whereas in this case it is not Boolean. It is 16-bit signed because of the mistake we have already seen. This one, the value returned by a function having non-void return type shall be tested. Here we have a problem whereby we have declared the function foo to return a value, and this value is not tested, is ignored here. So let me go to 20.7. Expression resulting from the expansion of macro parameters shall be enclosed in parentheses. This is a guideline that is explicitly addressing the lack of parentheses around the highlighted occurrence of X. So, and finally, we have 22.7. The macro EOF shall only be compared with the unmodified return value from any standard library function capable of returning EOF. What is the problem here? The problem is that the programmer inserted a cast. So the result of getChar was casted to char before testing for EOF. And in implementations where char is unsigned, this means that EOF, whose value is -1, would be converted to an integer, a positive integer. So it is too late to compare with EOF here, okay, because of the cast that has been erroneously put by the programmer. Okay, so that's it for the small demonstration of the use of eclair to avoid costly mistakes. So a brief summary for this part. C is the most used language for the programming of embedded system. The advantages of C come with corresponding disadvantages. So this is the reason why we want to have language subsetting. MISRA C is the most authoritative subset of C for the development of critical systems, and it is an integral part of the software development process that has very little to do from bug finding. And keys for a smooth and successful adoption of MISRA C into an organization are two things: good tools that are qualifiable according to functional safety standards and proper training of the personnel. Okay, Vance.
Oh, very good, Roberto. That was fantastic. I will go ahead and take presentation back from you. There we go. Folks, that was Roberto Bagnara of BUGSEng, obviously an eminent expert on MISRA. Well, let's answer these quiz questions before we wrap it up today. We had the 6 questions. Look at these answers. They are all false. Indeed, all false. Number 1, software testing is the best method to improve quality? No. The best method is to prevent defects, right? Proper requirements, good code, prevent the defects statically before testing dynamically. MISRA. Number 2, safety critical domains provide good information and recipes for C coding? No, not at all. How many possible C code constructs are there? Infinite. Exactly. That's why we have MISRA. Number 3, humans think they're effective. Oh, yes, they think they are, but that's not the question. Are they effective and efficient in reviewing and optimizing C code? Not really. Humans are good at reviewing requirements, designing. Machines are much better at statically analyzing source code. MISRA. Number 4, with great static code analysis, no other verification is necessary. If you had perfect design and perfect analysis, you could make the case for not needing further testing. But how can you prove you had perfect design, perfect requirements, perfect software? You can't. So prevention is much more efficient than detection. But detection, that's the testing. Are there errors? Is still necessary. Number 5, dynamic software testing is similarly efficient and effective as static analysis. Oh, we only wish it were. Static analysis has been estimated by experts. Dr. Barry Beam, USC, Kokomo, yeah. He says preventing defects is 700% more cost effective than detecting and fixing the defects. And number 6, verification and validation are similar. Oh, not at all. Remember, verification, does implementation meet the requirement? Validation, do I have good requirements? Are they correct, complete, unambiguous, and verifiable? Validation, verification. Yin and yang, helpful, but not the same. Well, folks, that concludes it. And we've gone a few minutes over. We have time for a couple questions. Let's see. The first question, Roberto, are there any tools available? Do you have recommendations for MISRA C tools? That's an interesting.
Well,
that's a fun question.
I have an obvious conflict of interest for this. So my company produces what I believe, and because I'm one of the main persons behind it, that is very, very good. So I would suggest go with Eclair.
A great tool, Eclair is. Thanks, Roberto. Being fair as well. And another question. Is static analysis cost effective in terms of application? I'll go ahead and try that one. You know, you can pay a lot of money for tools and it takes human time to use the tool. But compared to the debug time, you know, if you're interviewing someone for a job and they say they spent hours debugging their code before, that means they're probably fairly inexperienced, to be honest. We've all had real bad mistakes. Think of us, C programmers. How many of you have not had a C pointer error? We all have. How many of you have not had a bug that you couldn't fix overnight? Yeah, we've all had those multi-day debug sessions on the intermittent bug. Many of those, the great majority, not all, but the great majority could be found by static analysis. If you have free labor, then maybe you can make the case for less static analysis, but none of our labor is free, and our projects, aren't they always almost behind schedule? Yeah, we have aggressive schedules, so I think it's very cost-effective static analysis, regardless of what you pay for the tool practically. Well, folks, we are exactly 5 minutes over time. And as you know, what do you call a safety critical project 5 minutes behind schedule? We call it a big success. So we hope this webinar was successful for you. And Roberto, thank you again for joining on AFuzion's monthly technical telecom and webinar series. Thanks, Roberto.
Thank you, Vance.
Thanks, everyone.
It was a pleasure. Bye-bye.
See you again. Bye-bye.